This is section 4.4, trigonometric functions of any angle. Here are the objectives of this section, and I actually really like this information because it all comes together. But the thing that is important is that we're going to evaluate trig functions of any angle and not just acute angles like we had previously. In many applications we encounter, there will be angles that are not acute. So, for example, there might be like a robotic arm that might have a range of motion of 360 degrees. So something a little bit different. Okay, so when we evaluate these trig functions at any given angle, it's still the same process. But now what you need to pay attention to is that theta, if this is the initial side, and we rotate to get theta, you can see that this is no longer an acute angle. Angle theta is actually an obtuse angle in this case. And so what we're going to end up doing is we will end up dropping a perpendicular, referring to this angle here, which is often referred to as theta prime. It's kind of messy. Theta prime, and it's known as a reference angle. A reference angle. And all of this is kind of shown here, but one thing I want to mention is that this R value is always going to be positive. So if you're looking at this, which I really don't refer to, you'll notice, but R is always going to be positive. So the definitions from the previous slide can be extended to angles that are not acute, and that's what we are going to focus on today. We've already talked a little bit about it because it is pretty important, but here are a few things to mention. So previously I have told you that sine and cosine are both positive here. And in the second quadrant, cosine is negative, but sine is positive. Here, both sine and cosine are negative. Here, cosine is positive, but sine is negative, right? Well, that's all this fancy chart is telling you. But some teachers like to explain it a little bit more. I think if you know each of these here, you'll be fine, okay, as long as you know how to use it. Some teachers like to say all students take calculus, which I would like, but I don't think is necessarily the case. So if you look at the first letter in each of these, here, this means that all of the trig functions are positive, because if sine and cosine are positive, everything is. Here, this is saying that sine is positive. Well, we already know that. This is saying tangent is positive. Well, we should know that because a negative divided by a negative is positive. And then finally, the C is telling us that cosine is positive. Well, again, we already know that. Okay, so however you want to remember this is fine, but it's very important that you know this is quadrant 1, quadrant 2, quadrant 2, quadrant 3, and quadrant 4, and which values are positive and or negative in each of those quadrants. And you'll see why it's important shortly. Let's take a look at this example. In this example, we have an ordered pair, just a regular ordered pair, where this is x and this is y. And it is a point on the terminal side of angle theta, drawn in the standard position. So if I go ahead and draw this, point P is 20, negative 21, which would be somewhere over here. Call this P. So this is on the terminal side of our angle, which means this is angle theta. Okay, so if that is angle theta, then what we will typically do is drop a perpendicular here, and we'll call this theta prime. And it's very similar. It's the reference angle, which we'll talk about a lot here in a couple slides, but I'm just going to get your feet wet here. Now, if this is the ordered pair 20, negative 21, x is 20, which means this side is 20, and negative 21 is this side because we'll go down 21 units. So now what we need to do is find side R, or the hypotenuse in this case. Well, just like before, we're going to apply the Pythagorean theorem to find that hypotenuse. So we will have 20 squared plus negative 21 squared is equal to R squared, or 400 plus 441 is equal to R squared, which is 841. When I take the square root of this, I get 29. Now technically, R is positive and negative 29 because when I take the square root, I really have a positive and negative result. So here, since R, I told you in a previous slide that R is always positive, so I just want this positive value. Okay. Now we are going to use this information and SOHCAHTOA to answer the rest of these questions. So sine of theta is the opposite over the hypotenuse. So we will have negative 21 over positive 29. And then we also want cotangent of theta. Remember, tangent is the opposite over the adjacent, so cotangent is going to be the adjacent over the opposite. So in this case, the adjacent is 20 and the opposite is negative 21. And there we have the answers. Why don't you give this one a try? Okay, so P is just an ordered pair from algebra. So if x and y are both negative, it's somewhere over here. Call this P. If it is on the terminal side, this means this is angle theta. But if we drop a perpendicular, we'll call this theta prime, which is the reference angle. It's basically the same thing. So the x value is negative 5. The y value is negative 7. We need to find r. And the way we find r is by applying the Pythagorean theorem. So we have negative 5 squared plus negative 7 squared is equal to r squared. 25 plus 49 is r squared. This gives us 74. When I take the square root of that, technically I have a positive and negative, but r is always positive. So r is the square root of 74. Now I want to find the 6 trig functions, so I want to find everything. It's sometimes helpful to write down SOHCAHTOA unless you have that memorized. So let's get started. Sine of theta, and again we're going to use this reference angle here. So sine of theta is the opposite over the hypotenuse, which we just found to be the square root of 74. When I rationalize this, I get negative 7 times the square root of 74 over 74. Cosine of theta, so using this reference angle, and again, reference angles come up more in a couple slides from now, but I just want to get your feet wet a little bit. Cosine is the adjacent over the hypotenuse. When I rationalize this, I get -5 times the square root of 74 over 74. Tangent of theta is 7/5. And then I can find the other the other three trig functions by taking these reciprocals. Cosecant is the reciprocal of sine. This is the square root of 74 over -7. Secant is the square root of 74 over -5. And then finally, cotangent is 5/7. And we're done. We've talked a little bit about quadrantal angles. Basically, these are the angles that occur on the axes. So this is 0, pi over 2, or 90 degrees, pi, or 180 degrees, pi over 3 pi over 2, or 270, and then back to 2 pi. Basically, we want to be cautious of these values because sometimes we're dividing by 0, which will give us something undefined. For example, here I want to find sine, cosine, and tangent for the angle theta is 90 degrees. So if theta is 90 degrees, I know this is my initial side. This is my terminal side because this is 90 degrees. I know that this has the ordered pair 0, 1, which means cosine of 90 degrees is 0, and sine of 90 degrees is 1. So we've already answered part of this. Sine of 90 degrees is the second value in the ordered pair, which is 1. Cosine of 90 degrees is the first. And then we want to find tangent of 90 degrees. Remember, tangent is sine over cosine. Anything divided by 0 is undefined. So tangent of 90 degrees is undefined. So this is just what we want you to be aware of when you're dealing with the quadrantal angles. So here comes the definition of a reference angle. Okay, so basically angle theta is just your standard angle. Well, the reference angle is the acute angle that is formed by the terminal side. For example, I can see here, and again, this is always the initial side. If this is angle theta, if I drop a perpendicular, the acute angle is the reference angle. So these happen to be the same thing in this first example. In the second example, if this is angle theta, I can see that this is an obtuse angle. It's bigger than 90 degrees. But if I drop a perpendicular, I can see that this angle is acute. This is my reference angle. The reference angle in this case is found by taking 180 degrees minus whatever this original theta is. We can also do this in radians. Here are a couple more examples. If this is the initial side, this is theta, I drop a perpendicular, so this angle here is my reference angle, theta prime. This angle measure can be found by taking 180 degrees. Since we're in this quadrant here, we will take theta minus 180 degrees. Because theta is more than 180 degrees, so we are going to subtract that out. Over here, this is 360 degrees, so we need to take 360 degrees minus theta. Now, you're probably thinking, how in the world does this work? I don't even know what's happening right now. Don't make it harder than it needs to be. Let's just kind of talk through this. Starting with 225. Now, if this is my initial side, 225 degrees is not quite 270. And I know to get to 270 degrees, this is 270 degrees. So 225 is more than 180, but less than 270. So 225 degrees is somewhere in here. So this would be angle theta. And it's 225 degrees, right? Well, basically, if I drop this perpendicular and call this theta prime is my reference angle. I want to find out what that angle measure is. The reason we have reference angles is because it will help us identify our trig functions much easier if we have reference angles. The reference angles are usually pi over 6, pi over 4, and pi over 3, or 30 degrees, 45 degrees, and 60 degrees, respectively. Okay, so if we have something that ends in a 5, chances are the reference angle is going to be 45 degrees, but let's just take a look. Here, I know this is 180 degrees, but we've gone beyond that. So to find my reference angle, I'm going to take 225 degrees minus 180 degrees. Sure enough, our reference angle is 45 degrees. All right, let's take a look at the next example. 11 pi over 6. 11 pi over 6 is not quite 12 pi over 6. So when I make a revolution, I'm going to end up in the fourth quadrant here. This is theta. So I'll drop a perpendicular. The acute angle is our reference angle, and we'll label it theta prime. I just need to figure out what this angle measure is. And the way I do that, in this case, is I take 360 degrees, or 12 pi over 6, since we're dealing with radians, minus minus theta, which is 11 pi over 6, to find my reference angle is pi over 6. Here's a shortcut for you. You don't even really need to draw a picture. Maybe at first it's helpful, but whatever this is a multiple of, since this is some multiple of pi over 6, that tells us that our reference angle is pi over 6. So you can draw it if you want to, but it's certainly not required. For example, in part C, I can see that this is a multiple of pi over 3, so that means pi over 3 is my reference angle. The reason this is helpful is I might say, what's cosine of negative 2 pi over 3? Well, it's going to be the very same thing as cosine of pi over 3. You just need to be careful of the quadrant. So let's look at this last one. Now this last one is more than one full revolution. It puts us here. So if we drop a perpendicular, and this is 390 degrees, well, I'll take 390 minus 360, and I get 30 degrees. So this reference angle is 30 degrees. Now here's what I was just saying. To find the value of a trig function, so any trig function given some angle theta, what I want to do first is figure out the reference angle. In other words, is it a multiple of pi over 6, pi over 4, pi over 3, sometimes pi over 2? Once you know what its reference angle is, then figure out the quadrant that the angle is in and assign the necessary sign to it. Okay, now much of this lesson is going to be using the reference angle and figuring out the exact value of a trig function. So I have lots of different examples, but they are all basically the same. So once you think you get the hang of it, then just pause each question, see if you can do it, and then check your work. Okay, here we go. So in this first example, we have cosine of 135. Well, if you want, you can sketch a picture. 135 degrees is here. So this is angle theta. Remember, we drop a perpendicular to the x-axis. This is our reference angle. So you just want to see how much further this terminal side needs to go to make 180 degrees. So basically you will take 180 minus 135 and you will find that it's 45 degrees. Again, if this is a 5, your reference angle is likely 45 degrees. Okay, now this angle is in quadrant 2. And in quadrant 2, we know that that cosine is negative, sine is positive. So if I find cosine of 45 degrees, whatever this is, we know cosine is negative in this quadrant. So I know that cosine of 45 degrees is root 2 over 2 because that's the associated ordered pair. But in quadrant 2, I know that cosine is negative, so cosine of 135 degrees is negative root 2 over 2. Let's look at another one. Now this one I'm going to try without even drawing a picture. Looking at this, 240 degrees is more than 180, which is here, and less than 270. So I know this is in quadrant 3. So I need to figure out how much I went beyond 180 degrees to get to 240. Well, that's 60 degrees. So my reference angle is 60 degrees, which is also the same thing as pi over 3. Once I know my reference angle, write down the corresponding ordered pair. 60 degrees has the corresponding ordered pair 1/2 root 3 over 2. In quadrant 3, I know both of these are negative. So my corresponding ordered pair becomes negative 1/2, negative root 3 over 3. And here's what we can conclude. Sine of 240 degrees is the same thing as sine of 60 degrees because that's our reference angle. But because we are in quadrant 3, we know that sine is negative. Sine is the second value, so this result is negative root 3 over 2. Here are many more examples, so just hang tight if you're not quite getting it. Here we're going to deal with radians. Now, I think radians are a little bit easier to deal with, but that's just me. Looking at this, 5 pi over 6 is not quite 6 pi over 6, and 6 pi over 6 gives us pi. So I know that we are dealing with quadrant 2. And in quadrant 2, we have a negative and positive for cosine and sine. Now I need to identify my reference angle. This is a multiple of pi over 6. Pi over 6 has the corresponding ordered pair root 3 over 2, 1/2. But in quadrant 2, the first term is negative and the second term is positive. So this is really the ordered pair that we're dealing with. Well, tangent of 5 pi over 6 is going to be sine of 5 pi over 6 over cosine of 5 pi over 6, which in this case is 1/2 over negative root 3 over 2. Once we simplify and rationalize, we end up with this equaling negative root 3 over 3. This happens to be one that you should memorize. Okay, this one. So again, this is a multiple of pi over 6. So my reference angle is pi over 6. And the corresponding ordered pair is written there. Now we need to figure out which quadrant this is in. Remember, if this is negative, we're going to go in the opposite direction, or the clockwise direction. This is not quite one full revolution because 11 pi over 6 is not quite 12 pi over 6. So when I end up making this revolution, I'm in quadrant 1. And in quadrant 1, both sine and cosine are positive, so this remains our ordered pair. Cosecant is the reciprocal of sine, and sine is 1/2. So we can conclude that cosecant of negative 11 pi over 6 is equal to 2 over 1, or 2 in this case. Pause this and see what you can come up with. My reference angle in part A is pi over 6, since it's a multiple of pi over 6. So I'm going to use this ordered pair. 5 pi over 6 is in quadrant 2. So in quadrant 2, I know cosine is negative. So cosine of 5 pi over 6 is the same thing as negative cosine of pi over 6. Using the reference angle, we know it needs to be negative, so our final answer is negative root 3 over 2. Part B. Negative 120 is in the third quadrant. To get to a negative 180, I need to go 60 degrees further. So my reference angle is 60 degrees, which is the same thing as pi over 3. That has the corresponding ordered pair 1/2 root 3 over 2. In quadrant 3, I know that both of these values are negative. So now all I need to do is find the cotangent of this value. So cotangent is cosine over sine. This reduces to a positive root 3 over 3. Part C has a reference angle of pi over 4 because it's a multiple of pi over 4. This corresponding ordered pair is root 2 over 2, root 2 over 2. Cosecant is the reciprocal of sine. And the quadrant, let's see, this is not quite 8 pi over 4. 8 pi over 4 is equivalent to 2 pi, which is one full revolution. So it's just shy of that. So we end up in quadrant 4. In quadrant 4, sine is negative. So we want the reciprocal of negative root 2 over 2, which is this. When we rationalize, we end up with negative square root of 2 for the answer here. I'm hoping you're getting the hang of this by now, but we'll throw in a few more examples for good measure. Here we have cotangent of 540 degrees. Now this is a big number. I can see it's more than 360 degrees. So it's more than one full revolution. Now what I'm going to do, so we talked about some angles where we could add or subtract 360 and their equivalent. So if I subtract 360 from this, I end up with cotangent of 180 degrees. These two angle measures are the same, okay, because they're multiples of 360. So 180 degrees is right here. And I know this ordered pair is -1, 0. So I can find the cotangent of that. Cotangent, remember, is cosine over sine. In this case, this value is undefined. Example of a quadrantal angle. All right, this is a multiple of pi over 3, which means my reference angle is pi over 3. Pi over 3 has the corresponding ordered pair 1/2 √3 over 2. 5 pi over 3 is not quite 6 pi over 3. 6 pi over 3 would be one full revolution, so this stops just shy of that and puts us in quadrant 4. In quadrant 4, I know sine is negative. If I want to find secant of 5 pi over 3, secant of 5 pi over 3 is the reciprocal of cosine. Cosine is 1/2, so this is equal to 2. There you have it. We're going to take this a little bit further. Same type of thing we've done, but just a step further. So now it says find two angles between 0 and 360 degrees where cosine of theta is equal to -√3 over 2. So if I want two angles between 0 and 360 degrees, that means our answer needs to be in degrees rather than radians. So let's talk about some things we know. We're given cosine of theta is -√3 over 2. Well, when I think of cosine being equal to √3 over 2, I think of cosine of pi over 6 or cosine of 30 degrees. Because pi over 6 or 30 degrees has the corresponding ordered pair of √3 over 2 1/2. So that means cosine of 30 degrees is √3 over 2. Okay, well, we need to be cautious because cosine is negative in our given information. So if I think of when cosine is negative, again, you can think of all students take calculus if you want, but I know that cosine is negative in quadrant 2 and in quadrant 3. So remember, all students take calculus. This is the positive values. So cosine is negative. And again, you can just think of the ordered pairs in quadrant 2 and in quadrant 3. Well, this is basically my reference angle because I want to find two angles between 0 and 360. So to find the angle in this quadrant, I will take 180 minus my reference angle of 30, which is equal to 150 degrees. 150 degrees does in fact have a reference angle of 30 degrees. So this is one answer between 0 and 360. Furthermore, if I want to find the angle in the third quadrant, I can take 180 degrees plus 30 degrees to get 210 degrees. This is another angle that has a reference angle of 30 degrees. Both of these angles result in a cosine of -√3 over 2. And both of these angles are in fact between 0 and 360 degrees. Not so bad. Okay, so this one, you'll see something like this in your homework. So let's just kind of analyze what's going on here. We are given sine is negative root 55 over 8. Okay, now if sine is negative, I know that sine is negative in two quadrants, quadrant 3 and quadrant 4. So I know this given angle or this given value is in one of those two quadrants. But when I read on, I see that cosine of theta is also negative. So cosine is negative in these two quadrants. So I need to find the overlap, and the overlap happens to be in quadrant 3. So given this information, I know that I am dealing with quadrant 3. And when I answer these two questions, I need to make sure that they have the appropriate sign for quadrant 3 angles. So let's just sketch a picture of what we're given. We know that we are in quadrant 3. I also know that I'm given information regarding sine, or I'm sorry, yeah, sine. So TOA. So if this is sine, this is the opposite, this is the hypotenuse. Okay, so I'm going to drop my right angle. This is my reference angle. Call it theta prime. I don't care. Now, one of these two values is negative, not both of them. I've told you that the hypotenuse is always going to be positive. So in this case, this is positive 8. So the opposite is going to be negative root 55. Okay, so now let's find this. Let's call it angle X. The Pythagorean theorem. I'm going to wave my hands a little bit here and just tell you that this becomes plus or minus 3. Okay. Now, in quadrant 3, I know that I'm going to go left, which is a negative value. So this is going to be a negative 3. So let's apply SOHCAHTOA and find cotangent. I know tangent is opposite over adjacent, so this is the adjacent over the opposite. So in this case, it's going to be negative 3 over negative root 55. When I rationalize, I get positive 3 root 55 over 55. Cosine. And cotangent should be positive in the third quadrant, right? Cosine in the third quadrant should be negative, so when all is said and done, we need to make sure it's negative. We have the adjacent over hypotenuse. Boom, fantastic. I have put this slide in to, again, reinforce how important these identities are, but it's also important for the next example. Now, this example can be made easy, and it can be a little more difficult. Since we have been asked to use the fundamental identities, it becomes a little more complicated with more work involved. And I have provided you the identities in the previous slide, but hopefully you kind of feel a little bit comfortable with them, and you'll see where these come from. So let's see what we're given. We are given information regarding secant, and we want to find tangent and sine. Okay, this quadrant 4 will also come in handy, and I'll show you why. All right, well, let's think of our Pythagorean identities. One of them is tangent squared of theta plus 1 is equal to secant squared. Well, I'm going to plug in what we know, and what we know is secant. So this becomes tangent squared plus 1 is equal to 41/40 squared. All right. Squaring this, I'm actually going to subtract 1 from both sides. I'm just going to try to make this a little bit faster. So 41 squared is 1681 over 40 squared, 1600 minus 1. Okay, now when I subtract 1 over here, that's like subtracting 1600 over 1600. This gives me 81 over 1600. I'm then going to take the square root of both sides, make sure I have plus or minus. So tangent of theta is plus or minus 9 over 40. Okay, now you're probably wondering, well, is tangent positive or negative? This is where this quadrant 4 comes in handy. In quadrant 4, tangent is negative. So we know that tangent of theta is negative 9/40. We have just solved one of these. Now, when we try to find sine of theta, sometimes it's easier to use what we just found. However, if whatever you just found, if that answer is incorrect and you use it to find the next answer, both answers will likely be incorrect. So what you want to do, and I know it's a little more work, is you want to go back to square 1 and use only the given information. So when I do this and I want to find sine, well, let's think of this trig identity. Cosine squared plus sine squared is equal to 1. Now this comes to mind because I want to find sine, and what I'm given, secant, is the reciprocal of cosine. So this is my best approach here. So with this being said, I'm going to take the reciprocal of the given information to get cosine, square it. This plus sine squared of theta is equal to 1. So I'm going to subtract that from both sides. So I have sine squared is equal to 1 minus 40 squared is 1600 over 41 is 1681. So I can write 1 as 1681 over 1681 and subtract. So sine squared is equal to 81 over 1681. I will take the square root of both sides. Don't forget the plus or minus. So sine is equal to plus or minus, in this case, it's going to be 9 over 41. And you need to figure out which of these two you want to use. Well, in quadrant 4, sine is negative. So our answer is negative 941, I guess. And there you have it. Now, this problem is just like the previous problem. So we can use fundamental identities, or we can use an alternative. And I think you'll see that the alternative is a bit easier, but in a case study, if you're asked to use a fundamental identity, make sure you do so in order to earn full points. But here's an alternative approach. So it says that this value for sine is in quadrant 4. So when I sketch this, it's over here. And SOHCAHTOA helps me identify the given values. If this is equal to sine, this is the opposite, and this is the hypotenuse. The hypotenuse is always positive, which means this is negative 5. Oops, call this x. We will find that missing side using the Pythagorean theorem. For the sake of time, you should find that this is 12. Okay, So if this is 12, I want to find cosine. So cosine of theta is the adjacent over the hypotenuse. We should know in quadrant 4 that cosine is positive. This ends up being a positive result, so we are happy. Finally, let's find tangent. Tangent of theta is the opposite over the adjacent. In quadrant 4, tangent is negative. Boom, we're done. As you can see, this is quite a bit faster than using a fundamental identity. This concludes the material for section 4.4.